Lucija, Čoga, predstavljam slikovni elipsometer v slovenščini. Lucija mislim, da je najmlajša predavateljica do zdaj, po mojem bi kar ostala najmlajša znotraj tega leta. Prosim, Lucija. Še to, no, mogoče tisti, ki jo ne poznate, je dela doktorat, od leta 2011, pri profesori Ireni Drevenšek-Olenik na, pa povej sama na čem, ker smo v angleščini napisali, da nam je narobe v slovenščini povedala. Je noter, tako da. Lahko govoriš v slovenščini, če želiš? Kakor želiš, ne? Jaz mislim, da njime vse en, ampak tujcev danes ni. Lahko pa govoriš tudi v angleščini, ne nobenega problema, če ti je lažje.
Thank you for the introduction. This seminar will be given in two parts. In the first part, I would like to give you a brief introduction into imaging elipsometer and elipsometry. And after this presentation, Luka will demonstrate how this equipment works. So, what does elipsometry measure? The concept of this technique is characterization of thin films and bulk materials by using polarized light. The name of this technique comes from the fact that light that is reflected at angle from a surface usually has elliptical polarization. So, if we take a look at this picture, we can see that polarization state of the incident light can be decomposed into two components, P and S polarized light. In the case of P polarized light, the electrical field oscillates parallel to the plane of incidence, while in the case of S polarized light, the electrical field is perpendicular to the plane of incidence. So the sample of the surface differentiates between this polarization, which causes a change in the polarization state of reflected light. So the linearly polarized light is transformed into elliptically polarized light after its reflection from the surface. So in elipsometry, the measured values are expressed as psi and delta, which are denoted as amplitude ratio and phase difference between P and S polarization. Elipsometry has a lot of advantages. For instance, it is a sensitive and non-destructive optical technique. In contrast to other optical techniques, elipsometry measures relative light intensities instead of absolute light intensities of P and S polarizations. And therefore it is very reproducible, robust and accurate technique. For instance, we don't need to use any reference sample, and it is quite insensitive to scatter and fluctuations. Another very important or remarkable advantage is that elipsometry measures a phase, which is highly sensitive to very thin films. And with this technique, we can measure thickness down to a single atomic layer. So, elipsometry also allows a determination of various material characteristics, including complex refractive index and dielectron constants, and then thickness of monolayers, multilayers, and bulk layers. It can also measure surface roughness, optical anisotropy, and composition. Because these measurements take only a few seconds, we can perform real-time observations of various processes. For example, etching, oxidation, thermal annealing, and so on. Okay, here is a picture of our imaging elipsometer. This device was funded by the Center of Excellence in Nanoscience and Nanotechnology, and to my knowledge, this is the only imaging elipsometer in Slovenia. This device consists of sample handling stage, Z stage, and active anti-vibration system. It also consists of two elipsometric arms. Inside of these arms there is a light source and a set of sensitive optical elements such as polarizer, compensator, and analyzer. There is also an objective and CCD camera. Polarizer and analyzer are actually the same element. Only difference between them is that polarizer is responsible for the polarization of the incident light prior to its reflection, while analyzer analyzing the change in the polarization state of the reflected light. Compensator is also a very important element because it is used to shift the phase of one component of incident light, and in this way the linearly polarized light is transformed to circularly or elliptically polarized light. Here are some additional photos of this equipment. Here we can see the other components of imaging elipsometer. For example, spectroscopic box with xenon arc lamp inside and electronic box, and there are also computers. This equipment is located next door to focused ion beam, so in the basement of building B. So imaging elipsometer is actually the combination of ellipsometry and microscopy, because in contrast to conventional ellipsometers, it contains objective and spatially resolving camera. The objective images the illuminated area of the sample onto the camera, and as a consequence, the areas that have different optical properties cause different signals in the camera image. Our imaging elipsometer is based on null ellipsometry. This is the procedure of finding a minimum in the signal of photodetector. This means that optical elements are rotated so that there is no signal on the photodetector. But usually the compensator is fixed at a certain angle, while polarizer and analyzer are rotated. From the relative angles, we usually then obtain psi and delta values. This procedure is very time consuming and slow, but nowadays every software enables automatic knowing. As a light source, we can use a xenon arc lamp with tunable wavelengths in the range from 365 to 1600 nanometers, or solid-state laser at 658 nanometers. In the case of xenon arc lamp, we can perform spectroscopic ellipsometry, while in the case of solid-state laser, we perform laser ellipsometry. The specialty of our system is the extension to near-infrared region, which makes our system very useful for investigations of semiconductor materials. The lateral resolution of the system varies with used wavelength, and so the elipsometric measurements in the UV region can be performed with lateral resolution of 1 micron, while at larger wavelengths the lateral resolution is lower. So from the ellipsometric measurement, we would like to obtain physical properties of our material, but since the psi and delta values cannot be transformed directly to this, to the thickness or to optical constants, we have to construct an optical model. In the optical model, we should consider thickness and optical constants of all individual layers. And as the optical model is constructed, then unknown parameters, thickness or optical constants, are varied until a good fit of calculated values to the experimental data is achieved. So the calculating of ellipsometric data is very easily, can be done very easily by a Curian modeling software. In this software, there are three parameter definition sections. Material parameter definition section, sample definition section, and data and fit parameter definition section. In the material parameter definition section, we can define all the materials that are present in our sample. And so there are a lot of materials already in database, but we have also added new materials. In the sample definition section, we arrange these materials in the right order, and as the optical model is constructed, then a simulated psi and delta curves are displayed in the same place where the experimental data are. Then thickness or optical constants are varied until these simulated curves fit to our experimental data. With our imaging elipsometer, we can also perform Brewster angle microscopy. This microscopic technique is very useful for imaging of monomolecular films at the air, at the gas liquid or gas solid interfaces. Here is shown the principle of this microscopic technique. So if the light is incident on the surface, for example water, at Brewster angle, then for polarization there is no reflection. So in the case when we have just clean water, we obtain dark image. But if the thin film is introduced in between two phases, for example air and water, the optical properties of the system change so that a small amount of incident light is reflected. And this can be seen as a brighter region in the Brewster angle microscopy image. So in the combination with Langmuir-Blodgett technique, we can study morphological features of the films at the air-water interface. In this case, a small amount of surface active molecules are deposited onto clean water surface, and in the beginning the density of the film is so small so that the molecules behave like they are in gaseous space. But then we compress this monolayer with the help, but by decreasing of the surface area with the help of these movable barriers. And during the compression, monolayer goes through different two-dimensional phases. At the end, we obtain a curve so-called surface pressure area isotherm, which is characteristic for each monolayer. Here is presented surface pressure area isotherm of staircases. In the combination of Brewster angle microscopy, we can observe what is really happening with our monolayer during the compression. So in the beginning, when the molecules are in gaseous phase, we can observe small islands of surface active molecules floating on the surface. We can observe different structures. But when the surface area is decreased, monolayer becomes more dense, and domains with different intensity appear. We can also observe these interesting zigzag patterns, which indicate that the heat chains of staircases are not oriented perpendicular to the surface, but instead of this, they are tilted in arbitrary directions. In the solid phase, these patterns and also domains should disappear, but I don't have any pictures of condensed phase. So if someone wants to know more about imaging Elipsometer, here are some of the technical specifications. And for more information, you can go to the Center website. And if you have any questions or you want to perform some elipsometric measurements, here are the contact emails. Okay, this is all from
Okay,
my side.
thank you. Does anybody have some questions?